טוב, תודה שבאתם למיטאפ, זה המיטאפ ה-12, אני מנסה לספור, אם אני טועה אז אל תהרגו אותי. אני ממש שמח שבאתם לכאן בהתראה כזאת קצרה, אני ממש שמח לראות שהעולם מלא, למרות שאמרנו שהמיטאפ הזה יקרה כמו לפני שבוע. אז וולקאם לישנים ולחדשים. המיטאפ הזה יתעסק בפרססנט ממורי על ידי דוקטור בנויט הודזיה. אחר כך, מה? בנואט. Sorry. בנואט. I'm so sorry. ואחר כך אני אעשה סדנת קודינג קצרה על virtual file systems. מי שירצה להישאר, זה שיש חדרת פרטים זה יהיה פלוס. כן, אני מבקש להשתיק טלפונים וכיפה. סליחה, שכחתי, ביקשו ממני כאן להגיד שבאוגוסט מתקיים אירוע אוגוסט פינגווין, זה יקרה בחמישי לשני בבאר שבע. לשמיני, סליחה. בחמישי לשמיני בבאר שבע. אם אתם רוצים לקבל עוד כמה פרטים על הכנס הזה, אז גוגל את או תכנסו דרך האתר של עמותת המקום.
Hi, thank you. So it's going to be in English. So first thing, I'm French. I live in Ireland. I work for an Israeli company, and I tend to pick up the worst part of any accent I encounter. So yeah. So if you don't understand me, stop me, ask me. If I go too fast, tell me to slow down because I tend to just stupidly stop picking up speed quickly. If you have any question at any point, just ask also, don't be afraid. I'm probably more afraid than you than the other way around. So, let's start talking about persistent memory. What we're going to look at today, we're going to look at the NVMe evolution, which pretty much means paradigm shift from the async storage I/O memory access to a sync model. Then I'm going to look at the persistent memory Linux software stack, then how to use it, emulate it with Linux, then how to do actually remote PMEM, because when I like to break stuff, I like to break it remotely. So actually, it's because it's nicer like that. I'm a distributed system guy. And then maybe a little bit look at the micro storage architecture. That's something I've been toying with for the past year. So let's start. NVMe evolution, persistent memory. Yesterday, I would say, in the past, I think even like 10 years ago, you used to have the gigabyte solution, which was RAM with memory packed, with battery packed system. And we kind of moved on to NVDIMM with RAM and flash based system. And it's basically on power down, everything's copied back to flash, and when you power back up, everything is moved back up to RAM. And just a reminder, NVDIMM is basically what you put in the DIMM slots. And emerging NVDIMM technology that we actually start appearing is PCM for phase change memory. HP is big into that. 3DX point from Intel. Hardware vendor already have access to it. The product are going to arrive next year in 2017. Memory store and kind of things like that. It's a kind of paradigm shift because it's like almost 1,000 times faster than your non-tech, and it's like really closer to RAM. What that means is the persistent memory kind of characteristic from the software point of view. It's a synchronous model. It's like accessing memory. It's load, store, memory instruction from CPU. There's no paging, and you basically have a reasonably CPU stored CPU. Okay. Why is that? So what's happening? Over the past few years, we've been shifting from the classic SATA model, and then we got the NVMe introduction. If you've been at the E8 talk a couple of weeks ago, they presented the whole NVMe stack, which is actually really nice. It's very close to the actually RDMA model, and you get, I would say, past the 50-second microsecond barrier. However, when you actually do that, you start seeing that your software stack and block I/O stack become responsible for the bigger part of your latency. And you're also bounded to an asynchronous memory model, which is the RDMA model. You put everything in a queue, everything in RAM, and then you actually trigger the action, everything is pushed to the NVDIMM, and you get your completion. And if you look at the NVMe asynchronous model, because you have such latency, some guys in 2012 actually did a little bit of research and realized if you actually do active polling rather than actually waiting for the MSIX interrupt back, you're able to shave 2 to 4 microseconds, and you're actually faster and more performant when you do the active polling, which is a sync model, rather than actually doing the async model with MSIX. And hint, the SPDK Intel library that use the user space NVMe use that model. And that pretty much means that when you start moving to the new model of the new hardware that's coming for NVM, it becomes even more obvious. That's the actual number that comes from Intel. If you do NVMe with the 3DX points, you're 7 times faster, but if you actually do the direct persistent memory access with the load store, it's 1 microsecond access time. The key difference is you're doing a 4 kilobyte read and you're doing a 64 byte read, which is your cache line literally. What does that mean is there is going to be a shift of moving away from the classic block I/O model access. You have your software trajectory. If you actually stick to the block I/O, you're going to be sticking there, and you're going to start seeing more and more persistent memory optimized system that will be shifting away from doing big block access to directly byte addressable memory access for persistence. And that's why we started appearing in the Linux stack a new tiered software stack and a device driver and a solution like that. We used to have, and what's going to happen now more and more is we have the indirect I/O access with, which is basically existing applications that are just going to access and behave normally and just leverage the underlying new NVM system. After that, we have the indirect PM access, which already exists, which use the DAX and the ML, and for Microsoft, which is DAS. It's partially changed to actually benefit from the optimization of a persistent memory, and the future one that start to appear, but mainly in academia, like Nova file system, PMFS, and that kind of things like that, we are purely optimized for persistent memory byte addressable access. However, there is some challenge with byte memory access. Remember, you're doing direct load store from CPU. Load store and CPU are optimized for consistency. When you do your store by example, you don't know where your data, your cache line is going to be, where it's going to actually be, and it's actually persistent only when it reaches the NVDIMM. It can be stuck at any level in the cache or at the memory controller of your NVDIMM system. And to solve that problem, you have different ways of dealing with it. You can actually do your full cache flush, which is actually not really optimal. And Intel started adding new functionality to the CPU to solve that issue. They have cache of optimized flush, allow more concurrency. This one is really nice, which is the cache write-back access, which means you still maintain your data in cache, but you guarantee that you flush it down. And however, you still need to do your p-commit just to make sure that your memory buffer are being flushed and not stick there, and just in case actually if your power goes down and kind of thing like that. Last but not least, you have the asynchronous DRAM refresh. That's kind of a legacy system a little bit that came from the old NVMe legacy system when you had a flash and RAM. And that was a signal that was sent to them so they can actually flush everything to the flash while they still had some power left. Okay. So this thing, durability, is really the big problem because you start doing memory access the normal way, you expect everything to be persistent, but you still need to manually actually deal with that. There's no library that are coming in to actually help you handle that, but you need to be aware of that, especially if you're going to do very low-level Linux kernel development. So, let's look how actually persistent memory looks like in a software stack. You need to have a Linux kernel 4.2 at least. Anything below probably won't work, and everything actually there's a lot of bits missing. It's still heavily under development. The main thing is, I would say, for doing PMEM, it's DAX. It stands for direct access. used to be called XIP for executing place. And it literally allows you to mem map your PMEM in user space or in kernel space, and then you can actually do direct memory operation over it. Under that, we have the BTT, which is block translation table. That's for legacy application. I'm going to deal with that a little bit later. That's for classic I/O operation if you want to do it, because remember, we're dealing with cache line now. What happens if you're going to write, let's say 2, 3, 4 cache line in a row, that you go for 1K write. Since you're actually doing that kind of write, you cannot guarantee that everything will be written at the same time, because the CPU can reorder and do all the stuff like that. So you end up having a problem with that, and that's why BTT exists. That's mainly for legacy application. Then you have block, window driver, PMEM, which are low-level PMEM management, and then fit core, which are actually for the device management using SCPI version 6. How does that look when everything fit together? You have the SAPI and feed for the management, for actually loading up the different devices and kind of things like that. That's your legacy application that are going to rely and use the whole persistent memory system NVMe. And then we have the DAX file system, which is actually really nice, allow you to literally just expose your file system, then you actually map it, and then do direct load and store via the MMU. I'm going to explain how to do that a little bit later. So, important thing, BTT versus DAX. BTT provide atomic sector update semantics. That means if you actually write a cross cache line, they take care of that. It's literally the block I/O level. And it's there for applications that still rely on sector while not being torn, and they can still work the normal way. So it's for legacy application. DAX, it's for direct access, low mapping of PMEM range, directly access in user space. For example, you can do your load and store, mem copy, everything. And if the application is aware of the persistent byte addressable modem, it will manage it and everything by itself. So it's literally just an easy way to access it. So last but not least, you have to remember, so far, PMEM are not backed by page struct. It means you cannot do DMA to it yet. It's direct PFN access. And that means there's some limitation there. But once you're aware of that, you can go around it.
What is PFN?
PFN, it's page frame number. That's the actual hardware address of the persistent memory. So most of the time you have the page struct, and then you actually do, which is your virtual address, and then you're walking down, you get the PFN and you write to it. The PMEM is addressed by, if you use DAX, it's actually a direct access. When you map it, you use the PFN address of the NVDIMM. And that's why if you don't have the page struct, you cannot do the DMA. But there is a patch since March 16 that has been proposed for doing that from Microsony people, specifically for that. Yeah?
You said that the BTT provides sector semantics, and
yes.
You showed before that ext4 has a DAX interface?
Yes, it has a DAX. It means that you can actually use ext4, XFS, and ext3 with DAX.
Don't you need the sector semantics?
Not anymore, because they actually created the chance specifically in ext2 and ext3 and ext4 for directly using DAX. So it means they added the code specifically to be PMEM aware, not being block aware. So you actually go through, instead of going through the classic block I/O, you actually go straight up to the DAX, and then they actually make sure that you can, when you do the msync, memfence, and everything else like that, it will happen within ext3. And you don't have to go through the classic block I/O level. When you go through BTT, what happens is you actually do your block I/O write, and then they actually guarantee that all your cache line, when they write and everything, you don't actually lose any data at any point, which means also it's slower. So I think some guy did some experiment last year. Is if you use BTT versus DAX optimized, you have like a factor of 30 to 50% performance difference. So, using emulating PMEM on Linux, that's where the fun parts are. Yes?
I just wanted to comment that DMA to persistent memory does work.
I'm going to talk about it.
There's a zone device. You're going to talk about zone device?
Sorry?
The zone device. New zone memory or device memory.
Yes, you can do, there's a patch set for doing DMA to persistent memory that was proposed. It's not in Linux kernel for doing that. But you cannot do that without the patch set. So, for example, if you, there's no PCI bar exposed yet, or that kind of thing like that. New hardware will be able to expose it.
Not PCI bar.
Yeah.
Normal DIM. I think it. Well, my recollection is that it is mainline in 4.6.
Last I recall, no, but I need to check that because I had a call with a guy from Microsoft and he actually told me they didn't get it in yet. So, because the big problem with that is a big security issue. So if you have a link or a pointer to it, I would be happy to get it. So as I said, you need kernel 4.2 and advice, try to enable the NVMe dynamic debug. It will save a lot of time if you want to debug anything. Don't worry, I will share the slide deck so you will have access to everything. Then you need to pick your PMEM. So either you're part of one of the hardware vendor, Lucky One, or SAP like I used to work to and you have access to hardware, or no, if you're like me and you have kids, you're going for the virtual option or the emulation option, which is either by a hypervisor, RAM as persistent memory, or you can use the PCM SIM from, I think it's from Stanford, they did for emulating phase change memory, so you can also inject latency and that kind of things. Emulation, RAM, that's probably the easiest way. It's literally adding a kernel boot parameter, like mmap 16 gig, 16 gig. It's 16 gig of RAM, starting at 16 gig, and when you do your, when it's loaded, when you do LS, the PMEM, you basically see everything you have, everything actually presented there. It's really easy to do. QNU, not yet in upstream. I don't think they actually got everything in yet. You can also do the full NVMe emulation in QNU. The nice thing, it's really nice for doing NFIT dev. The only problem is you cannot really do BTT or that kind of things like that yet. Now, once you actually reach that level, you can play with DACs. Only Extent 2, Extent 4, and XFS currently support DACs. And also the block size needs to match your page size. There's some work for doing huge page support. I don't remember yet if it's been there in kernel. Last time I checked, it wasn't there. So it's really easy. You have your PMEM you created earlier, you do MTFS, and then you mount it, and you're ready to roll. So what do you do next? Well, you just have to unmap it. It's literally open the device, and map it, and then you can do your mem copy everything directly to the system. It's that simple. Yes?
So I can work with files, right? I just work with the raw device? Or?
Yeah. No, you work with the mounts, the actually TNP DACs that you actually mount there. Okay. And that's what actually you work for. Basically, the file system creates the thing, and then when you actually mount it, and when you actually do your mmap, when you do your write DACs, we'll actually do direct access straight down to the PMEM. That's the very nice thing. It's really easy to do. However, remember durability, you have to do that by yourself. And it's a little bit of a pain. However, we're lucky. The guys in Intel did all the heavy lifting pretty much for you. There's the PMEM.io that they've been working on for a while. And they have a whole set of libraries that exists there for making your life simpler. You have, if you want to do the basic persistency handling, instead if you don't want to do your mmap yourself, all the things like that, don't do your flush. Like PMEM commit, they have a nice C function for that. All of that is actually provided to you. And on top of that, they have libvmalloc for transparently, dynamically doing allocation. PMEM block, if you want to do blocks, that means if you actually start to actually go beyond boundary cache line, PMEM log, PMEM object, transactional, all that kind of things makes your life easier. And a very nice example with KV store, trees, and hash map, and that kind of thing. And we start seeing many more libraries coming up, binding to Python, C++, and all that kind of things like that. However, there might be some limitation of what type of architecture is being supported. I think it's at the moment it's purely Intel at the moment.
So is that part of SPDK?
No, that's not part of SPDK. There's two parts in SPDK. You have the PMEM and you have the NVMe user space. So the SPDK is the combination of both. I think it's SPDK is kind of something really that the trend in Intel for moving everything to user space, where they want to have the TCP stack, the whole packet processing and everything, and avoid as much interrupt as possible, which is the problem that they start seeing with NVMe. With the software and CPU interrupt and everything else taking so much time that they're actually losing half of their time actually by just handling interrupt and actually doing transfer and that kind of thing like that. Okay, so now breaking things remotely. Because I'm a distributed system guy, I really like to actually, when I started looking at PMEM, what I was really interested into was, can I use that to actually do distributed persistent memory and do a nice thing with it? That was stemmed from some work I was doing in SAP, where we started with SAP HANA in MemoryDB. We needed 4 terabytes of RAM and no server was existing for actually really doing that. And so the idea was, hey, can we actually just start stitching multiple server together and try to use them in memory remotely? So let's look at the state of the art. Let's get back to NVMe. If you want to actually do remote storage fast, the best way of doing it is doing RDMA transfer, where you feed the data straight up to the remote RAM, and also feed the NVMe command straight up to the NVMe queue. That's your best option at the moment, and I think that most of the new startup, hardware startup around there, or storage startup are basically doing that. However, what we want to do is transition, same thing, from indirect to direct flow. We want to bypass the whole RAM part. What we want to do is do either DRAM or NVMe and straight up to the NVMe part, to the NVM part, the persistent memory part here. There is some interesting project that allow you to start being able to do that. Project done out from PMC, now Microsoft, and that allow you to do PCI to PCI access, and also NVDIMM. And then there's the patch sets on March 2016. That was a RFC that allow you to actually back the PMEM, the I/O memory with page struct, which allow you to then do the whole RDMA mapping, and then allow you to actually do the RDMA. However, you always have a challenge of durability with persistent memory. Since you're dealing with cache line, you're dealing with all that kind of things like that, you have a problem of making sure it's actually durable when you're doing your RDMA write, and then the visibility issue. You have two options when you're actually going to do your RDMA write, remote write to PMEM. One is the allocating write I/O with DDIO, which is the kind of standard way, and the other one is the non-allocating one. That's an option that doesn't exist everywhere, but I think some I/O, some RDMA cards enable that. It literally bypass everything and you go straight down to the NVDIMM domain. So here's the problem, the visibility point. So if you do the normal PCI wide flow, everything get there, some cache line get populated, and then you have data durability. Once you reach the memory controller, you have with ADR, you're durable, you're safe. If you don't have ADR, you need to really make sure you actually reach that point. So with the RDMA, DDN, DDIO, what you actually need to do is one RDMA write, go down there, and then you need to do an RDMA send with the list of cache line you wrote to, which is basically the list of address you wrote to, and trigger the CL flush and the P commit, which is actually not really nice, but that still works. The other version, which is actually really nice, but you need to have the capability to do that, is the non-allocated write, where you actually do straight down there. And how do you actually guarantee that it's being persisted here? After your RDMA write, you need to do your RDMA read back. That's the only way at the moment to do it. I think hardware vendor and probably Mellanox last time I heard might be working on providing functionality to actually avoid the RDMA read back, but we have to see how it goes. That's just a wild guess. Which one do you think is actually faster between the two for a 64-byte read? Oh, write, sorry.
This one.
This one, yeah. There's approximately, you have 8 microseconds, between 4 and 8 microseconds difference between the two.
And how many concurrent writes?
The thing is, you're doing approximately, actually you're bounded by the limit of your RDMA stack at that point. So that's, since it's really small, it's really different of your RDMA stack at that point. It's a 1 microsecond right here, so, or even less because you're going straight to the PCIe. So you're not really limited by the actual NVMe stack.
Is this thing transparent with the initiator, or like I have to go to the Verbs API?
This thing should be, actually last time I tried it, it should be transparent. But don't hold me on that because I know sometimes you have some quirk between the different things, so you need to actually test it. But you can actually try it. The code is public, and you can just load it up and try it. But here's the thing. Remember, the software stack and CPU access start to be the biggest chunk of your latency. And more, a lot of vendors and analytics people and things like that say, hey, we would like to do the processing in data path. We really don't want to go through the RAM. We don't want to use the CPU. We don't want to do that kind of things like that. We want to avoid the RAM buffer, which is kind of HMM style. We want to have the software fetch only what we need, which is basically if you want to do visualization, we just want to fetch what we want to see and nothing else. And so what they want to do is basically say, can we just talk to each other with bypassing everything? And there is a lot of work that starts to happen on that front. We have the new hardware that are going to come next year or the year after will be able to actually expose bar address directly. That means PCIe to PCIe access will be enabled with NVMe. There is the RFC patch for the DAX for DMA IO. And here's the last bit. It's been released last week, I think. It's the CCAX fabric, which is a collaboration between ARM, AMD, Mellanox, and I think some other guys, Xilinx. It's a fabric specifically dedicated for in-data path processing, which is it's a trend. I think that there's more and more people and company and enterprise that actually look at bypassing the CPU together on that front and going straight PCIe to PCIe. The only problem is it's a complete security nightmare, so that needs to be solved, but that's a separate issue. Now, here's one thing. Don't worry, the NVMe gravy train will still happen for the next 3 to 5 years because company software, it will take some time to move from the previous model, block I/O, to the persistent memory byte addressable model. It's not going to happen overnight. There is a natural evolution. That's a guess on my side. Is like show of hand. Does anybody know about Ethernet connected drive? 1, 2, 3, 4. Okay, I have to explain that. You have product called Kinetic by Seagate, or the other one from HSGT, or I don't remember that one, I always mix it up. It's basically a hard drive with an ARM and an Ethernet port. You can run a very bare minimal Linux on it. What's really nice is you can, for example, run your self-block device on it. And you can literally scale really well. In terms of power consumption, it's a fraction of your normal storage system. In terms of cost and maintenance, it's also a fraction because if your hard drive dies, it's your self-block device or kind of thing. You just take it out, replace it, it's Ethernet port, it's really easy to use. And that's the thing that is actually picking up. If you actually go to OVH, the company, the hoster, know that actually what the offer is, you can get your server and you can actually just say, I want to have 2, 3, 4 more terabytes, saying I have 1, 2, 3, 4, and you connect it over TCP, Ethernet, NVDE, whatever you want to use, and that's it, you're done. And they literally have racks of those hard drives connected via switch, and that's it, nothing else. That means you're actually shifting away from an hyperscale type of architecture. But the thing is, what I think is going to happen is you're going to have the same shift happening with persistent memory. You're going to start having very minimalistic it's a package system where you're going to have your NVMe, maybe the ARM processor, maybe a little bit of RAM, and your fabric, and they are directly plugged. You can run a bare minimum Linux on it, and either you can do direct PMEM, you can rearrange it how you want, put high performance, low consumption, low power, KV storage. If you want, you can actually plug a front end. That's what they're actually currently doing with the Ethernet connected drive. They put the self front end or an FSV4 front end. It's a scan, and then you can rearrange it on the fly based on what you need. If you ever saw the Stratoscale architecture slide deck from Intel, that's what they're aiming for. What they want is to completely disaggregate your system and having a rack with CPU, memory, storage, and just saying, I want a server with 10 gig of RAM, 2 terabytes of RAM, and the thing is literally piped real time for what you need. And that's what they're aiming. You look at the OmniPath fabric and that kind of things like that. That's, I think, the long-term strategic objective. That's why also they're pushing really hard in HPC, because that they allow them to literally play with a really highly demanding system. I'm going to share the slide deck. There's links to everything I talked about, patch sets, libraries, and everything. And then you can just play with it and see if you like it. So, thank you. Any question? Yeah.
Can you create partitions over that DAX device?
Yes, you can use it as a normal file system, all the things like that.
And what's the recommendation for how do you exactly divide that memory between different applications? Let's say I have 10 applications that want to use PMEM. So what am I supposed to do as a...
Here's the thing. You still have a NUMA machine. You can do interleaving, you can do things like that, but then you have to declare namespace on top of your PMEM. That's basically, if you go back here, that's you have the infeed core where you can start doing creating namespace, and then with the PMEM block diagram, things like that, you can actually then access it. So you're actually creating namespace that are stuck to a single NVD, and then you actually access it. And if you do interleaving, then you can start spreading it and kind of things like that. It ends up being like RAM, so you end up being bounded by the NUMA aspect if you have a NUMA platform. And there's not really any specificity beyond that.
Another question, how does it operate with atomics? I mean, what's the penalty there if I want to do an
There's
atomic?
no difference. The thing is, if you do the atomics, the only key difference is when you do your atomics, you do it at the CPU consistency level. If you want your durability, you need to do the management of all the stack on the side. So it means we can actually do, and that's one thing the Intel guys are doing in their library, they use transactional memory. They do the full transactional memory, and if something breaks at some point, they do the rollback. But if they actually at the end are able to do the full flush and p-commit, they know they're actually consistent and durable.
Do you have any details about this?
Sorry?
Do you have details about this implementation?
It's all in there. You have all in it at the end.
Or about the transactional memory persistence?
Yes, I can send you links on that if you want. There's actually example out there for that. And even if you look at the open source code from the PMEM, they provide you example in their code for that.
So these are transactions, not hardware.
No, they use the CPU hardware transaction for that. Yeah. But the thing is, you do your memory transaction. But the thing is, you still enrich the CF flush and p-commit. So you actually they just use that in order to actually once you do the flush and p-commit, your transaction is finished.
Once you do the flash, you do the transaction.
Yeah, that means that actually finished. The thing is, you count that everything has been done, everything is ordered, and the flush is done, and actually pushed down. I can send you a link that have a very nice example of how to actually do that.
And using
it's kind of like in progress, yeah. But the thing is, they're betting really hard on it. You have 3x point and everything else. They're just really pushing very hard. They've been pushing for that. It's 3 years and that. And that was SAP that gave the preview in 2012 on that. And they were really saw SAP and memory, all that kind of things like that as the best use case ever saw, because that was terabyte of memory. They need persons the HANA struggling with the IOPS picture storage system. That was really what the film then. We would see the start of non-sort of, I would say, PMEM solution coming out from our vendor next year, because already then had their premise of the things coming out. Yeah.
Except Intel VX to this Intel Optane, are there any other vendors that say that they will release
Yes.
products that are faster than RAM already?
Yeah, they have Intel PCM, question memory, it's not to expand, it's still in pipeline, it's not yet completed now. You have the memory store, one that's on, I don't remember the name of the company, but the thing is, the first one will hit the market, is entirely to the extent. Even if you look at the HP, the machine, you know, the persistent machine thing, we're still betting on PCM system, but they just released actually 2 weeks ago the thing that they're going to support the point, but it's come up before, I don't think. Yeah.
If I want to leverage a new hardware with my current software, so for example, DAX with DAX-enabled SFS, what kind of a workload will benefit from that? Is it the F-Sync style of construction?
That's the thing. If you're going to use extra file system and storage, I think that you will see for DAX optimized one, you will see a performance increase. You can get 15, 20, 30% benefits like that. But that's not going to be massive. If you look at the new, in academia research, they've been doing Nova non-volatile file system and PFS, kind of thing like that. You have up to 70%, in certain cases, 200% performance increase in that case. But I'll be honest, don't waste your time on file system, that kind of things like that. Go straight for pure PMEM access and actually design applications to help for that. Because if it's actually just been emulating what's been done before, it's a waste of time. You're basically burdening yourself on it. You're just optimizing what already exists. One could just move straight up to type of application. Okay.
You also talk about this on RDMA, so they are old, they are new.
But the RDMA part, it's extremely experimental. You can
But this will explode as a byte recipe.
it's old in byte recipe because when you do RDNA, you use 64 bytes access. You can actually larger one, but when you do larger one, but in that case, when you do RDNA over 4K bytes, when you actually going to send you RDMA send after, you need to send a list of every single cache and that corresponds to the 4 kilobytes range, and then do the flush for all of them.
64.
Yes. So you round it, it's memory, the byte address on memory, so you actually can shift from the block IO mentality to an actual memory type of access.
What kind of latency are we talking about here?
So, for example, for the RDNA feedback for Microsoft.
So if the memory latency is like 100 nano to 500 nano, and this says 4 microseconds.
No. The memory latency is it's the 4 microseconds once you actually send it. That's the word for that. If you kill them one after another one, you actually overlap a little bit the cost of that. But I would say you can,
latency remains, right?
Yeah.
My throughput might be high, but my visual latency from local NVMe access of say 500 nano just jumped from my.
Yeah.
That's like order of magnitude.
And compared to storage system, it's still way faster. It's so it's different. The thing is also you have to think about you're probably not going to actually do local access and that kind of thing.
But again, for this, you can separate storage from the
Yes,
computer.
exactly. Which is completing the kind of pure storage with their flash lay or DGN, what they actually do. They're coming Xeon with an ARM with the flash and trying to put application on the same storage package. Which economically from a point of view doesn't really make sense. It's really niche, probably going to last for 2 years, and the new application will come out anyway to be like for the
Application requires more than 10 kilobytes.
I don't know, most of the time actually see you on security that I have really good machine, but it's like sure that we had a Spark system, you just tell them, hey, you can just go X1 VM on Amazon one for 1 terabyte, you can just request of a single machine, you're way more faster than class of time. It's, sometimes it's just vanity. No question? Okay. Thank you.
Thanks, Benoit.